Lecture 2, Internal Microprocessor and its Architecture. The programming model contains 8, 16, and 32-bit registers. The 8-bit registers we are talking now about the Intel architecture. The 8-bit registers are AL, 8-bit, AH, 8-bit. We call this accumulator. AH are the highest bits, 8-bit. L, the lower 8-bit, the lower byte. So the whole accumulator is 16 bits, but it's divided into 2 bytes. AL, the lower byte, and the higher byte, H stands for higher. The higher byte is 8-bit, and A stands for accumulator. So we have 2 8-bit registers, accumulator registers. BL, BH, the base index registers. The same thing, we have here 1 byte and 1 byte for the lower base index, the higher byte, sorry, and this is the lower byte of the base index. CL and CH for count, this is the count register. DLDH, data register. The 16-bit registers are AX. So, as we said, the whole accumulator is AX. So what does that mean? It means we can use this accumulator, we can use it as a 1 byte register, either AL, the lower part of this accumulator, or the higher part, and we can use all of it as 16-bit 2 bytes. We call it AX. When we want to use it as a 16-bit register, we call it AX. The same thing for the other registers. So 16-bit registers, BX, this one, CX, the count register, and DX, the 16-bit data register. SP, this is one whole 2-byte register, 16-bit register. SP, this is the stack pointer. We call this register stack pointer. BP, BP is the base pointer, also 16-bit register. DI, 16-bit register, destination index. SI is the source index. IP is the instruction pointers. Flags is the flags register. CS also 16. We call this code segment register. DS data segment. ES extra segment. SS is the stack segment. FS is and GS are these two 16-bit registers exist only on the 83, 86 through the Pentium 4. These two 16-bit registers. So all of these registers are 16-bit registers. But from SP to the GS, we can use them only as 16-bit registers. The first 4 registers, we can use them as 16-bit registers, as a whole register, or each of them, or as an 8-bit register. These ones from SP to GS, we cannot use them as an 8-bit register, only 16-bit registers. The extended 32 registers, such as EAX, extended for the advanced microprocessors. We add another 16-bit, so we get this 32-bit register. EBX extended to base registers, ECX, EDX, ESP, EBP up to this one. All of these extended, see these in blue, and these two FS and GS registers, we find them in this version from 86 up to Pentium 4. Real mode memory addressing. Only the 8086 and 8088 operate exclusively in the real mode. The 82, 86 and above operate in either the real mode or protected mode. What's real mode? Real mode operation allows the microprocessor to address only the first 1 MB of memory space. So what's real mode again? Real mode memory addressing means using only 1 MB of memory space. This is the real mode. The first 1 MB of memory is called either real memory or conventional memory system. Segments and offsets. A typical assembly language program consists of at least 3 segments that we saw them in the previous slide. The first one is the code segment, CS, that contains the assembly language instructions that perform the tasks that the program was designed to accomplish. Data segment, DS. This segment used to store information, data, that needs to be processed by the instructions in the code segment. And the stack segment, SS. It's used to store information data temporarily. The extra segment, ES, used as an extra segment. A segment, what's a segment? A segment is an area of memory that includes up to 64 kilobytes. Remember that. What's a segment? Area, space of memory that includes only 64 kilobytes. The segment address located within one of the segment registers defines the beginning address of any 64 kilobyte memory segment. Let's explain this in the following example. These are the 4 segment registers. If we have this nibble, if we have this nibble 0000 in hexa 0 hexa and another 000, so now we have 1 byte 00 in hexa, 1010, which is 5 in hexa, and this 0100, 2 in hexa. So this is the contents of CS, the code segment register. This number in bits, as you see it, 16-bit register. These bits correspond to this hexadecimal number stored inside this code segment. In memory, at this address, see these digits 1, 2, 3, 4. Each of them, they are in hexa. Each of them is, each number of them, as we saw, is of 4 bits. So 4 by 4, 16 bits. Fine. So, but remember that in microprocessor we have 20. The address bus is 20. See, 20. So why we have here only 4 by 4, we have only 16. Now, let's have a look at this terminology, logical and physical address, to understand what we are talking about. There are 3 types of addresses. Physical address, PA. The physical address is a 20-bit memory address must be generated by the microprocessor to access a location within the first 1 megabyte of memory. So the microprocessor generates this 20-bit address to access a location within the first 1 megabyte memory. Why 1 megabyte? Because a 20-bit, 2 of power 20, this is 1 mega. Why the microprocessor produces this space of memory? Why? To allow it to access the memory. Therefore, the physical address can range from, you remember, 1 mega, this is the beginning address, 1 2 3 4 5 zeros, and this is the end address, the final address. So the space is the total space, the total memory space or location. Memory location is 1 mega that we are talking about, the 2 of power 20. So can access this location, these locations, the total of 1 mega of memory for the 8086 and real mode 8286 up to Pentium 4. The offset, second, the offset address, sometimes called a displacement. The offset address is a location within a 64 kilobyte range. Therefore, an offset address can range from 000 in hexa to 4Fs in hexa. The total is 64 kilobyte. This is the offset address. The logical address consists of a segment value and an offset address. Segment value, it takes it from the segment registers, CS, DS, SS, or ES, and an offset address. The code segment, one of the segment that the logical access construct its address to execute a program. The microprocessor fetches the instructions, opcodes, and operands from the code segment. The logical address of an instruction always consists of a code segment always, and an IP. Code segment CS and an IP. IP is a 16-bit register. CS also is a 16-bit register. As following, CSIP. So we write the logical address in this way, in this format. An example. We have this segment registers, CS, DS, ES, and SS, and we have the CS with this data. The data is 2500 in hexa. This data in bits, in binary numbers, is now in hexa 2500. Okay, to reach the memory, we should have also IP address. Say in the IP the data is 1100, this is a 3, 1111, this is F, 1011, this is F5, and 1001, that corresponds to 9 in hexa. So the total is this number in hexa. This is what we meant by logical address, and this is what we understand from this definition. So the logical address consists of a number, a 16-bit number. See, this is in hexa, 16-bit, but this is in hexa, so we see it in with 4 digits only. And the offset part, that's it, the IP part, the offset part, that we find it where in the IP register. Both of them give us the logical address that we see it in this format, And see, for example, this is in memory, this is our logical address, this place, this location in memory. So CS and IP, this is the logical address. The offset address is contained in IP, as we saw. In this example, it is, as we saw, it's 94F3 in hexa. Now, the physical address, we talked about the logical address. What about the physical address? The real life address, the physical address for the location of the instruction is generated in the following way. So, the microprocessor, we write an instruction, for example. The microprocessor sends this instruction to the memory. For example, we have this number in the code segment. What we do to find the physical address? The first step, look for the data, the 16-bit number inside CX, the data inside CS. This is the first step. Append CS with a 0 in hexa on the rightmost end. This is the CS. Second step, append 0. This is the 0 hex in hexa that is required to be appended. See, appended. This is the contents of the CS. We can do nothing with this. This is just for explanation. For what does this step mean? To add as a number to the left side. Why? The target is to find the physical address. The third step, add IP. This is the offset. We said that the offset, you find it where in the IP register. Then add the IP. How? This is the contents of the IP. You see, we will add it to this number, the contents of CS, and the appended 0 to the rightmost end of the CS. Now we can add the number 0 in hexa plus 3 in hexa, 0 in hexa plus F in hexa, and find the result. The result is, as you see, very simple. 5 in hexa plus 9 in hexa. This is 14, which is E in hexa. And we do nothing with this because this is 2 plus 0, nothing is there, 0 gives us 2. See how many digits here we have. We have 1, 2, 3, 4, 5 digits. And remember, this is a hexadecimal number. So 5 multiply 5 by 4, because each hexadecimal digit corresponds to 4 bits. So 5 digits in hexa multiplied by 4 bits. This gives us a 20. So this is the physical address. This is the logical address, and the physical address that corresponds to this logical is this one. We can replace it with the physical address. So this is the physical address that results from 20-bit address. From 20-bit. Remember, CS register has only 16-bit. IP register has only 16-bit. But the physical address is 20-bit. How we got it? As I just explained. So the resulting is 20-bit address that's called the physical address to access location within the first 1 mega of memory. The first 1 mega, the real mode. The lowest memory of the code segment is this one, the lowest one. What we did here, we started with 000. This is the offset, remember. This is the offset that we get it from the IP. Okay, and we add 0000, and as we said in the second step, we append here 0 to the rightmost side plus the offset. We got this 5 digits. This is 4 digits. This is 4 digits. We got 5 digits because we appended this one, this 0 here to the data or to the number of the code segment. We got this 5 digits, the 1 mega. We call this the lowest memory. Say the lowest one is here to this location in memory. See? But what about the highest memory of the code segment? The highest one, we write here the offset, the maximum one. Why we started with 00 and ended with 3Fs? Remember, this range from 00 to 4Fs, this is the 64 kilobyte that we explained in the previous slide. This is why we took this as a beginning address, this is as the ending address. And we will see the relationship with our offset here, the real offset. And this, again, we will apply the same steps and we will get this number. So we got this number that gives us the lowest memory or the beginning memory, and this is the highest one somewhere. This is somewhere here in memory, somewhere here. This is the 25. This is the address of the 25000 in hexa, and this one is the highest memory, and the total is the 64 kilobyte that corresponds to 4Fs in hexa. And see where is the IP. This is the IP. This is exactly the location of the previous example. It's inside the 64. So your location, you will get it always within 64 kilobyte of memory space. In real mode. The real mode is the 1 mega. The 64 kilobyte that you will find your location is within 64 segment, because they are this location is inside the segment, and this segment, the 64, is inside the real mode memory. That is the first memory location, the first 1 mega. byte of the memory location. This is the real mode. Real mode, the first memory location, 1 megabyte. Your location that consists of CS and the of the IP. This you should find it within the 64 kilobyte segment. This is the space, the memory space of the segment, because the segment is 16-bit. This is the 16-bit. This is the 16-bit. This is the 2 of power 16 that corresponds to 4F, that starts from 25000 up to 343Fs. So 1 megabyte, as we said, the total real mode that start from 5 zeros up to 5Fs. This is the 1 megabyte. Say this is the beginning address of the real mode for this one, and this is the ending one. That's it. We win. This is the real mode. Another example. Say it's given this this content, the content of the CS is this one, and the IP has this number, 60-bit, both of them. The logic that we need, it's required to find the logical, the offset, and the physical address, the lower range and the upper range of the code segment. Solution: we start with the logical address. We simply put this as the CS, the code segment, and this one, the IP. This is the logical address. Done with it. The offset address is this one. This is the offset address. This is the offset address. The offset address is inside the IP register, 16-bit register. And this is the physical address. You take this number, this one, and append 0. Add it to the contents of the IP, the offset, this one. This is the physical. The result is this number, 5 digits, 20 bits. This is the physical of the physical address, always the 20 bits. The lower range, what you do to find the lower range? You take the lower range of the segment. So you take the contents of the segment to find the lower address. Add the 4 zeros to it. Remember, the code segment, this one. You append this 0 and add 4 zeros only, you will find the lower range of the segment. This is the upper one. The same thing, you take the contents of CS, append 0, now add to the 4Fs. Why this number? Because this is the range of the segment. This is the range of the 16-bit segment that starts from 4 zeros and ends with 4Fs. This is why this is the lower and this is the upper. Why we need to find them? To find the address. The address resides inside these two numbers, inside the 64 kilobyte, somewhere here between this number, the lower one, 24F60, and the highest, the upper range, 34F5F. It's here inside these two numbers, this physical address. You can say this physical, or you can say also, you can take it in its logical format. It resides inside these two lower and upper range of the code segment. In the code segment, CS and IP hold the logical address of the instructions to be executed. The following assembly language instructions have been assembled translated, assembled means translated into machine code and stored in memory. See this example, this mnemonic move instruction. Move instruction, what does this do? We explained this in our first lecture. In the previous lecture, move instruction copies data from one location to another in the operand. See here, it copies the contents of the source to the destination copy. Don't confuse with the meaning of move in English. Move, it means to leave the place where you are and to go to another place. But here it means stay in your place, just take a copy of the contents of the source and add it to this destination. So in this way, after executing this after executing this instruction, both destination and source will have the same copy of data. Copy the source operand, you remember these both of them, we call it operands. Okay, copy source operand to the destination, operand. Move is the mnemonic, remember, or we call it opcode, the operation code. These both of them are operands, destination operand and source operand. The move instruction doesn't affect the source operand. As we said, it just take a copy of the source and put it to this destination. Example of add instruction. Say we need to add 25 in hexa to 34. So we will want to make an addition operation to add two hexadecimal number 25 and 35. We use first the move instruction to move this number to this register, the accumulator register, the lower part of the accumulator. We call it AL, accumulator, the lower byte. Okay, 8-bit registers. We use 8-bit because this number, it's 8-bit. We are not allowed to use bigger than 8-bit because this is the capacity of this register, only 8 bits. And this is 8-bit, 1 byte means 8-bit. So move the 25 hexadecimal number into AL. So the result after execution of this instruction is AL will equal to 25. Whatever was the number inside AL, this number will be replaced here inside the accumulator register, the first accumulator register. The second instruction will move the 34, the second number, the hexadecimal number, to another 8-bit register, BL register. We'll do the same thing. The third instruction will implement the required instruction, the required operation. It will add this number in the source with this number. AL, the result will be as follows. It will add the contents of BL to the contents of AL. The result will be stored inside AL. So before executing this instruction, this one, the contents of AL was 25. After executing, the result will be 59. The result of this addition, 59. This is the final contents of L after execution of this instruction, the addition instruction. So the program above can be written in a simpler way. AL, we moved AL25 to AL, copied it to AL, we loaded it, then we use this instruction. Instead of using two move instructions, we can use only one. See, the first one we loaded this number, any of them, 24 or 34, loaded to AL, then in source operand, you write the other number, okay, to add both numbers together using this. So in this source operand, you can write a number only. And this one already saved with this number. So the addition, the result is the same as the previous program, as the previous simple program, assembly program. Assembly language, let's have a look at some instructions. Move AL to 57. This will copy 57 inside AL. AL will be stored by 57. In logical address, how we see this in logical address? This CS and IP, say we have this number 1132 and the IP is 0100. For example, we have this location, this logical format of the location in logical format, you see. And the machine language, this will be translated to B057. We theoretically we have no idea about this number, about this machine language, but this is we use this for explanation, just to understand how this instruction will be saved, will be stored into the memory. So this number is our instruction, this instruction that's required to copy 57 inside AL. The second instruction is this one that will move 57, will take the 57 after execution. This instruction, this one, AL will have 57. The second one will take the 57 stored inside AL and will store it in BH. So both AL and BH will have 57. See how many bytes is this instruction. This instruction, this is 1 byte, this is 1 byte. Remember, each digit is of 4 bits. So the 2 digits, it means 1 byte. And this is the second byte, we have 2 bytes. We have 2 bytes. So 2 bytes will be saved in 0100, the first byte of this. The second byte will go to 0101 of this instruction, and it goes to the third address, which is 0102. So 2 bytes, the first one will be saved in 0100, the second byte will be saved in 0101, and CS will stay as is. Will stay as. So the first location will be 1132 offset 0100. The second byte will be stored in 1132 0101, will be saved there, and will go to the new address, which is 1132 0102. Why? To take the next instruction, the code of the next instruction. We'll see it now. This is the code of the next instruction. The computer understands this code. So this means this instruction will be saved also inside two locations, as we will see now. So code segment, to execute a program, the microprocessor fetches the instructions, opcode and operands from the code segment. The logical address of an instruction always consists of CS, and IP, the offset. Let's see this graphically. How things will be stored and moved inside the memory between the microprocessor in the left side. This is the microprocessor registers, and this is the memory locations. Let's clean the screen to have a clear image of what's going on now within these two instructions. CS is here, where in the code segment. IP here in the IP instruction pointer. Both of them, by appending CS with 0, remember that, we will implement the addition operation to get what? The physical address. This is the physical address of this logical address. See, this is the physical of this logical format address. Somewhere here, this is the physical location in memory here. Here exactly where your instruction, the code of your instruction will be saved. B0 will be saved here, the first part of your instruction. We have 2 bytes, so will be distributed into 2 locations. Because the data we have here is only 8-bit. This is why we are allowed to take only one part, because they are 2 bytes, 16-bit. If we have advanced microprocessor or microcontroller, we can save both of them here in this location. But because we have only the space, the width of the data here is only 1 byte. This is why we should use 2 locations. This is the first one. We stored the instruction, our instruction, the code, the machine language of the instruction here, and the 57 will go to the second location. See, this increased by 1 to go to this. See, 1. Actually, 1 because IP is increased by 1. So after storing this byte, IP will increase itself by 1. And we will get here the new address 111421, this one. So we'll go to the second location and we'll save the second part of the instruction, the code of the instruction. So in this explanation, we saved only the instruction, the code of the instruction, B057, but we did not execute the instruction itself. We will see how this will be executed inside the microprocessor and memory. The 57 here. The 57 is our number that's required to be copied inside AL. So after storing the instruction, we will execute what this instructions requires to do. It's required to copy 57 from the memory. So we understand now that 57 was stored inside the memory. This number, it means it's inside the memory. This instruction, it means take it from the memory, take a copy of it and store it in the microprocessor. Where exactly? In the accumulator. Where exactly in the accumulator? In the in AL, as it's required here, AL. So it takes it here and save it inside AL. This is AL in yellow, you see it? So after executing this instruction, 57 will go and store saved inside the 8-bit, because it's 8-bit number. This one in hexa 57 in hexa. 1132, this is the segment, and 0101 is this one. As we said, the IP increases itself after finishing this, storing this, and implementing this instruction. IP will increase itself by another one. It became now 0102 and will be added with CS. CS is fixed for 1132. The number that will change is the number inside IP, as we saw. It will increase itself and it will go there after finishing of this operation. It will go to there to start with this instruction, that its code is this one. This is the instruction in machine language of this assembly instruction. So this is the assembly format of the assembly language instruction, and this is the machine language that corresponds to assembly one. This assembly instruction, the machine language, this one. The second step is this is, see, it will keep two locations for this because it's 2 byte. So 1 byte will go here and the other part will be stored here. This is what we show it for you. See, this is the 88, the first part. It starts with the most significant byte, not with CS, with 88, to save it in the first location, 11422 in physical. This is the first location. And the second location, you remember, this 24, because IP will increase itself. We'll take the new location, that will be this one, 11423, to fetch the second byte, to save it here. After storing the instruction in its machine language form inside the memory, now it will start to implement this assembly instruction. It says take the contents of AL, which is 56, and copy it where here in BH, the 8-bit, the 1 byte base index register. So the first byte of the base index register, 57. So this is the final result. Again, you are not allowed to write here, for example, BP. You are not allowed to write here BP. Why? Because both registers should be of the same size. BP or SP or DI or SI, all of them are 16-bit, but this one is 8-bit. So you are not allowed to write in operands two registers of different sizes. Remember that. This table explains the segments in different microprocessors and the offset of them. This is the advanced one. Which ones you see? You can see here from 83, 86 to Pentium 3. These microprocessors have 30-bit segments, bigger than the first microprocessors. The first age microprocessors, 8086 up to 8286, and Pentium to Pentium 4 default of 16-bit. Their default is 16 bits with offset address combinations, as you see IPCS. Now let's have a look to another instructions and see. I will leave this for you to understand what I have explained in the previous slide, how the instructions, their machine code stored inside the memory, and how each instruction is executed in the registers or in the memory.